some participation points. Of course, I completely missed this. I'll put something together, something. Again, turn on your video so other people, when they talk to you or you're talking, you can be shown, and then hopefully you'll also be on the recording, show your nice face, and then of course rename so people can call you by name. It's good to always have a name to go by your face, and share your knowledge, which is what we're doing here. And I thought the format was good from last week, so I'll follow that format. We'll have a couple of kind of showcases, what I've done, where I'm stuck kind of thing, demo-ish. And then we'll just kind of plow through the notebooks of the lesson for video 4. And I don't know if there's any video lesson notebook for 5, being that that's the ethics one. I wouldn't think there would be that much, but anyways, if you guys know that, then we'll get to that next week. So with that, I'll start off with Cliff. Yes. I'll make you the co-host.
Okay, I don't know if I'm able to share my screen.
Let me stop sharing mine. And I think you start sharing yours.
Okay, I just want to show, I didn't actually get this to work, but I feel like I'm close. So I just want to kind of show how I was able to convert to ONNX. I guess PyTorch has a built-in method that lets you export your model to ONNX. So first I added these, and this only works for like a image classifier, these imports. So this imports the PyTorch libraries, and then you kind of run through your model, do all the learning, and you export it the same way. But the problem is it needs to when you reload your model, you need to load it without the GPU running. So I had to close out of the GPU, restart everything, and then load. I'm using the course 2. Then I re-imported them, and then you've got to come up with a dummy model input. So for an image, it's like this. This is the Python code, and so this is the shape of what gets learned. So for an image file, it will look like this. It'll be one batch for inference, obviously if it were more than inference, and then 3 channels, which is the RGB, and then the height and the width. So you just have to create it's just random numbers in this to sort of show what your input will look like. And then you can output it into this ONNX model with this path. And then there's just one more piece of code. Let me grab it. It's not in my Notion notebook. Yeah, this code will export it into ONNX. And so from there, then you get this model in an ONNX format, which is actually JavaScript. So these are just the imports for JavaScript. If you haven't really worked with it, this might seem a little bit unfamiliar, but this sort of converts the image into numbers. And then this algorithm, I found someone who had written a Lambda, an AWS Lambda, and a lot of this code I've adapted. I didn't write all this, but this just converts it to numbers like a tensor, similar to what we're doing in the MNIST part of the course. And then this loads the prediction. And then this just runs all the functions. But right now it's just it gives an error because I guess Fast.ai uses a custom head is what they said. And so I found instructions on the Fast.ai forums on how to remove the custom head, and that's my next step. Hopefully that'll work. The code is written for the first version of Fast.ai. I think we're this course is the first course in Fast.ai 2. So hopefully it'll work, but that's where I'm at with it. Hopefully, I think it's almost there, but yeah. Comments, questions?
That's nice. It looks pretty straightforward from at least the export part. My thing is I need to be able to export the ONNX models to my coworkers that are working in C# and C++. So I think I get to stop at the beginning of your part. So it's a little easier for me because then it's just their problem on the import and use.
Yeah, but I mean, they've got to know, because like this is like building that sort of like array, right? Where you're like averaging each pixel is like a number. So like here, this is like a JavaScript library. It's called ND array. So like they would have to have that in their language, I think, some way to convert those pixels to numbers. Because ONNX isn't doing that for you, you know?
Right. How big is the ONNX file?
It's 48 megabytes. So that's the reason why I went to it. Like AWS Lambda, I think has a 250 megabyte limit. And so 50 megabytes fits within it, but I think Fast.ai 2 doesn't fit within it. They had deployment instructions for Fast.ai 1 for it when they did, but I think that's the reason why there aren't any deployment instructions, but it may just be because it's new. Yeah, but hopefully if I can get this into Lambda, they're going to have to integrate it into their like C# code and everything, you're saying?
Yeah.
Can they just do an API call? Because like if you could just put this into a serverless function. Yeah,
they're highly resistive to using any models from Python. So it's going to be a struggle.
Sure.
It's just a bridge we haven't crossed yet. So this is nice to see like what your workflow is. I appreciate it.
Yeah.
So this is the model from lesson 2. You said you took your pickle file? Directly read the pickle file?
So what you have to do is it's the pickle file is just like exporting the raw Python, but this is actually like a PyTorch function. And so since Fast.ai just wraps around PyTorch, you have to like export it as like a PTH file. Well, actually you export it as an ONNX file, I'm sorry. But you export it from within PyTorch. So I export the pickle file, and then I import the pickle file back. And then this is just like a PyTorch command where you're dumping in your learner, and then you just attach .model to the like reintegrated learner.
Yep.
And I only say reintegrated because you had to shut off the GPU. But yeah, and as long as you give them like a tensor that's sort of the shape of the input, or that is the shape of the input, then you can output it.
Yeah, the model is specific to something of the specific dimensions. I didn't realize that the learner that you export is just Python code with a bunch of parameters. Until I tried to use it later, and I had some pieces that were missing. So it is Python. When you export
I think that's true. I put in the verbose thing. It's a lot though. It's a lot of parameters.
48 megs and hundreds of thousands maybe.
Yeah.
Sure.
You can turn on verbose. I turned on verbose, and it was pretty big. It was pretty long and pretty unintelligible. So, yeah.
Okay. Cool. Wow. That's good. That's good luck.
Hopefully I can get to work.
Yeah.
Do you load all the images for your training set at once, or do you break it up into those mini batches?
I think it does it automatically. It puts it in the mini batches because I'm just using the same thing as is in the notebook. This is just the result. So you know when you guys are doing the binder and the voila, like it's taking that same export and just using it for ONNX. So
why did you convert it to ones and zeros again? in your?
Here? Oh,
Yeah.
because so I have like another thing that I basically copied the structure of this model too, and so I want to be able to run it in production. And so to get it to run in production, I want to put it on a Lambda because it's super cheap to run like AWS Lambda. So it's the PyTorch files are too big to accomplish it. They're just very large. So I have to use AWS Lambda to cut the size down, or I have to use ONNX to cut the size down to run inference at a smaller level.
Does it make it smaller? Does ONNX make it smaller?
I believe so. I believe it does. Yeah, I think
You're
it'd be
saying smaller than a pickle file.
I think it's like all the different libraries that you'd have to run, not just the pickle file. It's like the container that it runs on has to be a smaller size. So.
Gotcha.
Right. So I think we're ready to move on to the next person, unless anyone else has any other questions.
No, I guess not. All right.
All right.
Then no. I just make you co-host.
All right. Can we see my screen?
Yes.
Yep.
All right. So I pretty much looked at the two further research questions from chapter 4. I didn't get too deep into them, but it's something to show. So the first one, as you can see here, was creating your own implementation of Learner. So that was kind of the wrapper sort of thing presented in chapter 4 that encapsulated the data, the network, the optimization function, the loss function, and the metrics. So first of all, I just followed the same approach from the book for getting the data processed. This was for MNIST, classifying just the 3s and the 7s. So just reviewing that, specify the path to the images, extract the images with the untar data, classify into the 3s and 7s, convert to tensors, stack, and then you make them into data sets and finally end up with a data loaders. I guess the first question that I had, I did take a really brief attempt at doing this whole process using the data blocks API while still using a custom learner. And it did not work at all. While I was able to do it just fine using one of the pre-built models, so using like the CNN model with ResNet, it worked totally fine using data blocks, but for whatever reason, using this custom version, I did not have a lot of success there. So just wondering if anybody gave that a shot, reproducing all of these many data processing steps using data blocks.
Nope.
Right. All right, well then that's all code that we've seen before. So going on to the learner itself, I used the same simple net that was used in the book, the same loss function that was used in the book. And then the rest of this here was basically an exercise for myself in using Python classes, which I come from R. R has an object system, but it's not, at the end of the day, particularly object-oriented. So I don't think you'll see anything here that is a major innovation as far as working with classes goes. But it's, my own learner class, you pass the data, the model, the loss function, optimization function, and learning rate to the class. And then it's got functions for calculating the gradient, training the epoch. And these, again, are all functions that we saw separately throughout the chapter, but packaged up into the class. The batch accuracy, validate epoch, fit, and then I threw in a reset parameters because I kept having to respecify everything when I wanted to see what was happening. And then in the end, instantiate the class with my own. And then I use the fit to run it a few times. So I'll go ahead and do that. Takes a second here because I'm running it locally. And then it prints out the validation accuracy and, you know, gets up to 97% or something like that. So again, it's no major innovations here as far as the deep learning goes. It was largely an exercise in Python class making.
Mm-hmm.
So I don't know if anybody else worked on that problem and had any insights to offer.
No, but I'd like to code.
Oh yeah, no problem.
Yeah, it looks like really challenging. It looks really quite an accomplishment.
So I guess stepping back, the biggest thing for this, the code itself, I don't think that there's really anything special about. Like, this really is just a repackaging of the code that was already written in the chapter into a class.
Yeah, but you had to go through the chapter and you had to
Pull it out.
put that into the class. And
Exactly, and that's
not as
kind of what you were talking about at the beginning, where the way the chapter is structured, it's very discursive. It goes off into a whole bunch of different, like, partially overlapping examples. So that was why this was pretty useful for me. In addition to figuring out the writing of classes, it was going through and figuring out, okay, what are the parts that are absolutely necessary to make the process work, and how do they interact with each other? So yeah, I'll throw this up on the Slack channel. But yeah, so like helper functions for calculating the gradient, those get used in the train epoch function. The validation is, I think, what's ultimately printed, and that uses the batch accuracy. So yeah, figuring out how all of these functions talk to each other, and yeah.
What's the backward?
That was a useful exercise.
What's the backward?
What was it?
Backward function on loss there. Where's backward come from? Loss dot.
Sorry, where?
Loss dot backward.
line 12.
Line 12.
Okay. Yeah, that's in the gradient calculation. So after you compute the loss, backward does the backpropagation. And that's where the gradients come from.
Right. Is that built into, I don't see the actual definition of backward. Is that just part of the?
I think it's part of Fast.ai.
That's,
That's, okay. Okay.
Yeah.
That's PyTorch. That's the PyTorch magic.
Okay. I mean, that's kind of what I was thinking. Yeah.
Yeah. I mean, from scratch. Yeah. There's definitely a lot of things in here that, that do rely on some of the built-in stuff. That would have been quite the feat on its own, I think, but.
It's very good.
Yeah, so I also looked at the second one, which was completing all of the steps using the full MNIST data set. I did not do that, but I did look at the full MNIST data set, and I ran it through one of the pre-built models. I think that this was useful because it, in these lines, I set this up using the data blocks API. If you saw in the Slack, I got very confused over the course of the last week about all of the data APIs. You have your data blocks, data sets, data loaders. There are data loader and data set from both PyTorch and Fast.ai with different levels of compatibility, and you can use data blocks to make things that work for one or the other pack. It's a lot. So I was really trying to figure out how to use all of these. So in this case, I did set up the data using the data block API. The one change from what we've done before, I guess, was that it used the grandparent splitter, and you had to specify that the train and valid names were training and testing, because the folder structure had a training directory and a testing directory. And then under those, you had, 1 through 0 through 9. And then under those were the image files. So it was the grandparent directory because it was 2 directories back. And then you have to specify the train and valid name if the names are anything other than train and valid.
That's awesome, Daniel, because I
so
struggled with trying to get back to 2 folders like before. I couldn't figure out that it was grandparent, so that's great info.
Yep. Good. I'm glad something about this is helpful because it felt like a lot of spinning in circles a lot of the time. But yeah, once I specified this, which we've seen it before, but I had to remind myself that when you're specifying the data block, there's no actual data specified in these lines. This is just a template.
How to get to it.
So after specifying that, then you initiate the data here with dls equals mnist.dataloaders, and then you give it the path. And then I'm not going to run this because it is local, and running the CNN takes a lot longer than running our little version on the sample. But all it took was this 1 line of code to get very good accuracy in 1 epoch. So, yep. And that's both of the further research questions. That's kind of what I spent a lot of my time on for the week.
Cool. Very good.
So if there are no other comments or questions, I'll pass control back.
I guess not. Very good. Thank you, Cliff and Daniel, for that. I think Daniel's way ahead of me. All right. Share screen. We'll do the who wants to be Jeremy. All right, so I guess this is where we end off in the last lection video. So then he does the loss function. So the way I'd like to do this is just if you're having issue, I guess, understanding, maybe you pipe up. Otherwise I'll just go ahead and shift enter, if you will. So we're gonna just start here. Is that okay, or anyone else wanna?
Good as any. Yeah.
Yeah. Okay. So
actually, can I ask Daniel a question? I'm sorry, guys. I'm trying to find the page in the book. Is it okay?
yes,
Of course.
Yeah. So Daniel, you said you used the validation set as a test set.
So just the way that the folder structure was set up, when you pull the full MNIST from untar data, it was split as train and test. It didn't have a separate pre-specified, at least the particular version of it that I pulled that way didn't have a separate pre-specified separate validation set. So I guess like if I were being really, really rigorous in doing multiple model comparisons and things like that, it would have been more responsible to reserve the testing set and then split the training set into training and validation. But
okay. Yeah,
I wasn't doing all of that.
I was gonna ask because, usually you save the test set. You don't use it during training at all.
Yeah, and yeah.
Okay.
Yeah, just in this case, I didn't think that it was, I thought 2 sets were enough. I thought training and validation were enough in this case.
Okay. Just wanted to make sure because, from the chapter 2, I guess, the way I understood it was split your train set into validation too. So, okay, I'm all good. Thank you.
Yeah, but most of the time actually because we're using well-known test sets or data sets like MNIST, most of the time we use the training and the validation. We use the testing. They call it testing, but we use it for validation. So it's usually on our own data sets that we probably would want to like reserve a test set. But yeah, for most of the exercises, we use the training and the validation. Although it's called testing, there's another one. I think, I'm not sure, MNIST sample, I think, where it has three folders, one validation, one training, and then one for test. But the weird thing is the test doesn't have like labels.
Yeah, because the test set is really for testing, not for validation.
Yeah, but it doesn't have labels. I mean,
I think
because
typically in those,
in real competition, that's how they measure your performance.
yeah, that's I think the reason is for Kaggle. You don't get the labels for the test set. You submit it, and then it'll tell you what the label, what the accuracy.
Yeah, and that's why you really pretend like your test set doesn't have labels either. So you.
But yeah,
that's why you.
What I did was I took a look at the data and just relabeled it because it was so small anyway. Yeah, but you can.
Okay.
Most of the time, it's divided into two.
All right, that works for me.
Hey, Daniel, a quick question. How many images was that in your full MNIST set?
I actually didn't look, but it was a lot, and it definitely caused my 2015 laptop to choke. Really, I should probably just do more on cloud compute, but I'm just stubbornly using my laptop for anything that it will technically run.
Yeah, I was pretty stubborn in the start too, but and I'm not super crazy about paper space, and I find it very difficult to get a GPU most times, but it is amazingly faster, faster.
Yep. I did do like the chapters 1 and 2 on the GPU with the GPU in cloud compute, and it was amazing just seeing the progress bar. Boom.
All right, any other questions, comments? Okay, so does somebody want to drive and I'll just shift enter here? So I have a quick question. Loss function, is that the same as cost function? I'm trying to calculate my overall score for whether it's predicting is meeting my label, right? So is the loss function like a cost function at the end?
My understanding is that the cost function is usually the average over all of the loss functions. So like a loss function would be observation specific, and then the cost function is the summation of all of the loss or the average of all of the losses.
Average. Okay.
Where sorry, Andy, and where do you get the term from cost function? I don't know if it was ever used because the term loss function is the one that we use all the time, but I've never heard of the cost function.
Yeah, so the cost function is used by Andrew Ng's course, and it's a cost function J. It's commonly used in machine learning terminology. So I think loss function here is the cost function J, because the formula, you can choose different loss functions. It doesn't have to be MSE, it can be RMSE, it can be L1 form. So it's up to you what you choose as a loss function or a cost J. It's a vocabulary difference. That's actually for me difficult here. I have to translate some of the variables here, like in Andrew Ng's course, it's Y hat, and here it's predictions. So if you translate the vocabulary, it usually helps.
Yeah, you're right. Minimizing cost. That rings a bell.
Yes, minimize cost. So we want to minimize the loss.
Loss. So,
Yes. So I believe
what,
it is the same as the cost function. But I could be wrong.
I think you're right. Where did it come up, Andy?
Oh, because I was trying to figure out this loss function, and then I kind of looked up, on Google on what is loss function, and then all of a sudden I just get this cost function.
Got it.
Yeah.
I'm not sure cost is loss, or
Yes.
am I looking at something else?
So
Well,
it's
then
mathematical notation. The Andrew Ng's course uses math notation. And when you study math, and they use a letter J, capital J, which is a cost function.
Then to Daniel's point, what would be the average of the loss over the whole batch or epic or training? Is that just another metric?
I just sent a link to the chat to a really good Stack Exchange discussion that I remember reading earlier this year on the topic that can explain this a lot better than I can. So I would recommend giving that a look.
Thank you.
But I think Daniel is right. It's the average over all the things. So I have to take another look at that. Okay. Sorry for that.
The way I understand it is the loss is just, well, the average loss or whatever is you can apply it to like a single sample, in which case it's not the average, it's the difference between the predicted over the, like, for example, the actual, yeah, right. So if your target is supposed to be 1 and your prediction is 0.99, your loss will be 0.01, right? So it's a number. So you can either take the loss for the whole batch, which you then average the loss for each sample. So that's the loss, right? That's a number. The loss function, on the other hand, is just a function that gives you the loss. So whether it's usually, you can, like, sometimes there's a parameter in the loss function called reduction, so that you can say, I want to return the average, the mean over all the samples. So let's say I have a sample of batch size of 64. I want to see the loss for each one of them. There's a parameter that you can pass called reduction. So it doesn't average. But if you pass the reduction, and by default, it does reduce it, it takes the mean of all of those. So yeah, basically, it's the loss is just a number. Whether it's averaged, it's usually averaged out over all the samples, because it really makes sense to just take the mean so that you can compare the loss across different size batches or whatever.
As a metric.
Well, when you're doing gradient descent, you have to work from a single value. So you have to,
Yeah,
you have to take the average loss
for the
and
whole
then
batch.
you take the gradient of that. So,
But when you're like looking, you want to see what the loss is for a single sample, then
yeah,
you just take a look at what the values are for each one.
sure, yeah. But when you're doing gradient descent, you need to combine all the losses for the batch and then take the gradient of that.
Mm-hmm.
Yep.
Thank you. Sorry for that.
You guys, by any chance, have a link to the Andy NG's course offhand? Everyone talks about it. I've never seen it.
Which one? He has many courses.
Deeplearning.ai.
Yeah, if you go to Coursera, just look for him. It's there.
Cool. Thank you.
Yeah.
Okay, so I'll just start. And if you understand, then I can keep going.
Okay, so did we figure out here what the loss function is? Where's the code? Can you show?
So I'm running this on the loss function, I guess, right? And then I'll
Okay.
keep going until I get to that. So this is in the book that we have. So everyone good? Because I think we're just, we have our X's and now we're trying to move this into a rank 2 tensor, is it? Yeah. Okay. I take that as a yes.
Yeah.
Silence is golden. I've never used the little piece here. So I guess that's a special thing in Python.
It's PyTorch.
That's a PyTorch.
Oh, it's PyTorch.
Yeah, that turns on the ability to do the gradients.
Yeah. Okay.
It's magic.
Yeah, so you don't have to do it manually.
Yeah. And do we just set the bias here as a init here?
Is it random? Or just setting it to 1? Just, I don't know. Let's see.
Yeah,
Random
what you're
size
setting,
one.
yeah. What you're setting is the shape of the parameters. So the weights 28 by 28, you're saying I want to create my weights, which are 784
Yep.
in size, and then the bias is just one tensor.
One column. Yeah.
Yeah.
Okay. A column that's 28 by 28 tall.
And
But
the
what
bias
is it?
is just to
Actually,
say-
that there's a if you go to the forums, there's a discussion on this 28 by 28 comma 1 versus if you take out the extra comma size, it'll still work, but it won't compute the gradients. There was this guy who had a lot of trouble. Basically, I think he missed out this inner parentheses when he wrote that, and it still worked. There was no error, but just that he couldn't like train. So there's a very
Yeah.
subtle.
Yep. It expects a tuple.
Yeah, because there's actually another parameter. If you go to std equals 1.0. So when you take out that that extra tuple, the 1 goes to the std, which is also equivalent, except this is a what do you call this? A float, and it's gonna be assigned to an int, but it doesn't matter because the std is gonna be multiplied against rand n, which is a float, so everything turns into a float anyway.
Right.
But there's a subtle thing. The size is now 28 by 28, whereas the other one will be 28 by 28 comma 1, which size is like not necessarily a number. It's the shape. It's like a matrix versus a vector. So if you notice, there's a double what do you call this? A tuple. So it'll create a matrix of 28 by 28 by 1. So it's a column vector of 28 by 28 rows by 1 column. Whereas if you take out that one, it'll just create a vector, a rank 1 tensor.
That is subtle. You're right.
Yeah,
The
somebody was like,
Yep. The tuple. So on
the extra parentheses made a whole lot of difference. So in this case, the second call bias is gonna be 1. So it's just gonna be a vector. Actually, yeah, just a tensor, a single rank 1 tensor of
Yes,
1.
yes. You don't want a scalar in there. You don't want a scalar. You want a tensor. You need that one. And so the tuple that's being passed into init params is the variable size, which has to be a tuple, or should be a tuple, when it gets used by the return function. And the standard equal 1.0 is defaulting to 1.0.
Yeah, exactly. So it's
It
very
has
subtle.
the equal sign. When you have an equal sign like that, it's not a required parameter.
Yeah.
Boy, that's subtle. Yep.
Yeah, I know. Somebody was like, took him the longest time to figure it out, and somebody pointed out, yeah, those are 2 different things.
So to tease that apart, you'd have to break out this function init params and do a bunch of shapes, kind of getting some stuff in front of you. Wow.
Yeah. So it's a very subtle thing. So, like, it took him the longest time to probably tearing his hair out, trying to figure what was wrong, and it just was this missing parentheses. So
Yeah. So I actually went through that phase too. I had missed out the tuple, and like there was, as you said, there was no error at all, and things the matrix multiplication worked fine. The thing it did not do was so it did calculate the gradient descent, but it did not add it up. Right?
Yeah.
Like when you change with the data with the learning rate, that's when the magic didn't happen. So it took some time to figure that out, because it is very subtle and like very easy to miss out this in a continuous passing vector. And the problem is that the matrix multiplications were fine. I mean, at the end of the day, it did create a column vector. Right? It's just that it is not the type of vector that was expected. But it does, like if like the second one bias, it's a scalar that you pass in, right? And so the calculations go on still fine.
Yeah, actually, that's the thing. It's like we couldn't figure. There was no error, but it just didn't train.
Ooh, I hate that.
So, yeah. So I guess just helping out people, especially the good. One thing we should be able to do is start from a new notebook, start it from scratch, and try to write it down on our own, because it's a good exercise to like really understand what the code is doing. If you're just running it all the time, it's like, yeah, you kind of assume that you understand, but if you try to write it from scratch, it's a very good exercise to see what your understanding is, and then the fact that you have to go back and check what do I need to do next. Then it reflects that, oh, maybe I don't understand it that well yet.
Yeah.
So writing this from scratch is a very good exercise.
Yep.
Yeah. Yeah, it is.
All right. Continue.
So the bias is just a scalar, but it works because it will cast properly.
Yeah, some broadcasting is happening there. So
Okay.
in the earlier.
Okay.
It's actually a tensor. So it's a tensor
Yeah.
of rank 1. So it's not a scale. A scalar is just a number. So it's a
Tensor of rank 1. Yes, you're right.
Yeah, rank 1 tensor.
That's what I meant. Yeah. There you go. Thank you.
So that's the loss function.
Yeah, that's where the loss function is. And it takes the mean.
Any questions here before I continue?
Wow.
So now we're on the sigmoid. So I guess we're just calculating between 0 and 1.
Yes.
And I'm just gonna
This was cool.
plot that. So I'm just gonna add that in. Everyone cool with that?
Yes.
How it's done.
And now you have your gradients and your mini batches. Yeah.
What is?
So if I change this shuffle to false, or I leave it out, does it just take the first of my data?
I don't know. That's a good question.
Yeah, probably.
And then shuffle, just randomize it.
It might be random.
Correct.
Just try it out. It's easy enough to run. Okay.
Yeah.
I think that's the default.
Yeah.
Take a look at, do the shift tab thing, where you can see the defaults.
And the default is false. So shuffle is false.
Ah, default.
The default is false. Okay.
There's actually a different shuffle function.
So you
Also,
try to run it again and again.
Yeah. Okay.
Yep.
And we're gonna do everything here, right?
Did you guys see what the difference between the data loader and the data set is? Because that's a subtle thing that he kind of went through it pretty quickly, but try to understand what he's doing. Because this is the difference between what the data set and the data loader is. And this is exactly what's being passed.
So the main differentiator for a data loader is that it handles the batches, right?
Yep. And not only that, if you notice the data set, he did an enumerate string ASCII lowercase. So what an enumerate does, it's a Python thing where it creates a list of tuples. The first one contains the index, and the second one is the original list, the item in the list, right? So the way we use data sets is actually very similar in that we use the inputs and then the target labels as the second element in the tuple. So that's what we pass. So when we pass something like pass something to the learner, we actually start with the data set, which is a list of like files and their categories.
The
Right?
labels.
Yeah, what the prediction, the target label is. So in this case, you pass it a couple of two items. The first one is the input, and the other is the target label. And then what the data loader does is, if you notice, it groups all the inputs into one batch, into one tensor. and then takes all the matching, what do you call this, target labels, and groups them all into another set. So it's not just like batching them together, it's actually grouping all the inputs together and grouping all the target labels together into a matching, another tuple.
Sequence, another sequence.
Yeah, a larger tuple of each batch. So this is a very subtle thing, but it's very important down the line. So just notice that the goal, the data set is basically just a list, if you think about it. But the way we use it is we use usually, it comes out as a list of tuples. One is the input, the other is the target. And the data loader groups them together.
Mm-hmm.
And then the fact that we usually use shuffle equals true means as we loop through the data loader and ask for it a batch, it changes every epoch, right?
The ordering of them.
Yeah, it groups them. You read through all the samples once, but you
They don't
the
go
way
like,
you read them is not in the same sequence every time.
kind of picks at them in some weird order.
Yeah, so it's random each time.
Yeah,
and that's the reason why you don't
Right.
get values or like the loss each what do you call this? Every time you rerun the fit, even if you start with the same set of random weights, because of the data loader being shuffled, it will compute a different loss each time.
Also, I would like to say that data set is more like a convention that we use to group the X's and the Y's together, whereas I believe data loader is an object that we pass to the learner. So, the model expects that, like the Fast.ai model is built that.
Be this way, yeah. And remember, this is Fast.ai specific. This is not PyTorch specific.
Yeah.
Datasets are
Yeah, but
like
data set is like, yeah.
Datasets are like lists, and data loaders are like batches. I think Daniel is right in that sense. But also, the way it would move from dataset to form a data loader, and the way it groups them together is not just like, oh, I'll just take everything, group like one batch of dataset items and then group them. It'll actually split them into two tuples.
Right. You need the labeled data to be exactly lined, exactly matching.
Yep.
That's that's a very core principle.
But yeah, this short example, it's kind of glossed over, but later on, it'll help you understand better what's going on.
Hey. So now we put all those little sample together, right? Is there a batch size that's default, like 256, or whatever your?
The default is 64, but he increased the batch size to 256.
You just
Then how much memory you got?
You just keep going until you run out of memory. Is that it? So it's 128.
Oh, as to what will guide you to use a large batch size?
Yeah.
Actually, there's discussions down the line, but yeah, normally you're limited by memory, but there's also some discussion later. So don't worry about like what batch size. It's gonna be discussed. What's the advantage for using large batch sizes versus small batch sizes? Aside from like, yeah, GPU memory. The way I usually use it is I'll try to see a large batch size if I can until it runs out of memory, just because it's faster.
But I think your gradient calculation becomes more accurate with a larger batch size as well, because you're capturing more of the space when you calculate that gradient. And so you kind of want to tend to capture more of the physics of what's going on, and then but then you're size limited. So,
but there's also a disadvantage later that you'll see with large batch sizes, in that you know how stochastic gradient descent like tries to go to the lowest minimum. If you have too few batch sizes, it might not have the opportunity to like reach the lowest minimum yet, because you just have too few batches. So it depends on the data. Like, so you have to think about the data, the amount of data that you have, the batch size, and because there's also the relation to the learning rate. Because if you have large batch sizes, you want it to reach the minimum as quickly as possible. So there's like trade-offs, as I said. It'll be covered later. So it's not just the memory. Although in general, there's nothing wrong with just playing around, trying to see what batch size would run. I mean, yeah, it's something that you could experiment with.
Thank you.
But I have a question here regarding the statement. So you say that if you have less data, then it would not scale well, right? But I think it's at the end of the day, if you run more epochs on it, if you run the model a few more times, right, it gets the data. Because
Yes.
anyway, it's random. So, I mean, it would tune the parameters if you run more epochs, right?
Yep. But yeah, just as I said, it's going to be different for each data set. So the best thing is just play around with it, play around with the batch size. It's not always the recommended thing to like always use the largest batch size, especially if you have don't have lots of data. And it also depends on things like, well, can I use data augmentation to like, because the problem with running with too many epochs is there's this tendency to overfit.
Yeah.
So it's like, again, it's one of those things that like you only learn it after you played around with like running it again and again with different batch sizes until you're getting good results. So there's no one big, although in general, if you have a more powerful machine, of course you want to try larger batch sizes. Yeah. So there's nothing like a general rule. Yeah, what you do is you play around with it, experiment.
Okay. Shall we continue?
So Dave, this is where that the boss.backward came from in my class implementation.
Yeah.
It was literally just that method.
The back propagation of the loss function is the gradient.
So everyone cool with that? I don't know why we give different.
So that was one thing that I again, just getting all twisted around all the different data APIs and data models and whatnot. When I did implement the class, I put the training and validation data loader, plural, into one data loaders object. So when I was writing these functions, I would be doing, so in this case, it would be like xb, yb in DLs, and I think it was DLs.train.items maybe. Like there were methods within the data loaders to access the individual training and validation sets. Just, you know, trying to piece out how all of these data structures interact.
And I think that's the reason why you kind of want to try to implement on your own, because there's a lot of things hidden in Fast.ai. Like suddenly it does this, and I don't understand why it does that. But if you start with your own code, with your own implementation, you kind of, okay, this is what it's doing, and this is the effect. Once you get it running, especially, and then you can compare it with what Fast.ai is doing, then it's a very good learning experience. Because there's a lot of things hidden in Fast.ai that you only realize after you, like, sometimes you bump into things and you're wondering why it does that. So yeah, it's a very good exercise to try to implement these things on your own.
So I shouldn't abandon Fast.ai now that there's a Torch implementation out in R.
Oh,
It was announced today.
I think
I'm so excited.
You can call Fast.ai though. I saw this article a long time ago where you can call Fast.ai in R.
Yeah, there is. Especially in our studio, they've made a lot of efforts for Python and R kind of interoperability.
Great. Yeah.
They're all false. Oh, okay.
The last 4. Oops.
I guess if they're all false, they're all 0.
I guess.
So we end that section.
Yeah, and that's pretty much what I put into a fit method in the custom learner class, was that for loop.
Mm.
Yeah, and if you notice, it reaches 96.91 accuracy, which is pretty good.
For one epic.
But aren't we just doing 3s and 7s? Any other question? So we'll just keep going. Yes, no?
Sure.
Great job.
So why are we creating an optimizer?
This is where the init params is being applied, this 28 by 28 comma 1. Yeah, going back to that init params.
Oh.
That's something I was kind of spinning my wheels over briefly when writing up the code, was like, where did the init params go? And then I realized, oh, it's actually built into the nn.linear, and so it's not something I need to do on my own.
Yeah, but take a look at the parameters of linear, because again, it's the subtle thing. This is not the 28 by 28 comma 1 comma 1. The 1 is actually I don't know, what is it? Can you run the shift tab to show the default?
Variance, standard deviation. Yes.
Yeah. So the one is not, yeah. The one here is not the shape. It's the one for the,
STD equals.
And then this creates a vector by default. Just takes in the like how many rows do you want. It creates a column vector by default.
shift tab, I think, or question mark. Inside the parameter, inside the parentheses, do a shift tab. There you go. So in features, out features. So in this case, out features is going to be 1. The bias is a Boolean figure, and by default, it's true. So we don't need to create the, you know how we separated in the previous example in the init params where we created one for bias, but in the linear model, by default, it creates a bias. So this is equivalent to exactly that same thing with the tuple. So the one here isn't for the bias. It's for the out features, which is the one with the, if you go back to the init params, it's the tuple 28 by 28 comma 1. The one there is the out features.
Right, and it looked like it include bias is true by default regardless.
Yeah. That's
So
why
it's
we didn't need to
initializing
specify.
that.
Yep. So yeah. So if you take a look at the implementation of our init params and the way they implement linear from Torch, this is equivalent. But if you're wondering why there's a comma 1 there, this is the comma 1 there is the out features.
In the number of output, like if the number of inputs it take is 28 by 28, and the number of output it produces is 1. Just as number 1.
Yep. Exactly.
As we go along, actually we have a simple net which is which has 2 layers, with the one being 30 by 1. So like in that case it would be a 30, not a 1.
Yep.
Mm-hmm. Yeah. It's one output from that layer.
Yeah. It's actually the way I usually visualize like layers in the neural network. Is I think of them, the weights as like the connections between the inputs, the previous layer, or maybe the input. So the weights, like if there's 28 by 28, so I imagine them to be like 764 lines, and the out features is like how many neurons do I have, or output, like outputs. So in this case, we have one neuron interconnecting to 784
inputs.
And then you have, for each neuron, you have a bias.
Sure. That's the activation function, right? The one thing that all of the inputs are connected to.
Yeah, and then it usually gets connected to the activation function, the ReLU, which is normally doesn't have anything trainable anyway. So it's connected one for each. One input, one output.
It's the firing mechanism. The ReLU is a firing mechanism.
Yeah, because if it's above 0, it'll trigger. If it's below 0, it's 0. Yeah.
Okay. Gonna have to speed it up, guys. We're
Yeah,
gonna
no.
everything. So this is just PyTorch's way of handling our gradient, our stochastic gradient. Is that what I'm doing here? Because I see that, right? It's just data.
Yeah.
learn, and then that's it. So that was the same exercise except in PyTorch. Is that what?
Actually, that's Fast.ai. Learner is a Fast.ai.
Oh, yeah.
Built on top of PyTorch.
Yep.
Yep. You go.
You made it to
Right.
the end of
Good.
4. Any questions on 4? Okay. Oh, great.
Oh.
Okay, now we're back to our image classification. So it's pretty much the same things right here. And then this is Daniel's thing on data blocks. Should we stop and explain a little bit here, or everyone good?
It's pretty straightforward.
So this is
Really didn't get very much into this chapter, if I'm being honest.
So this is just like the setting it up, but it's not actually running, right? I mean,
Right.
and then when I'm actually calling is it doing the resize when I'm calling it? Are these firing off here? These item transform and batch transform, are these firing off when I like, where?
Yep. When you actually,
You know what I'm
So
saying?
the data block is just a template, as Daniel said. The data loader is connects the template with the actual set of data. Like it creates a actually it doesn't run it yet. It actually executes it when you ask for a batch from a data loader. So it doesn't execute anything actually at this point. It doesn't load anything. It's when you ask for it in the put it in a loop where you want the batch. So you type in 4xbyb equals in DLS. That's when it'll give you a train that DLS.train something. That's when it actually does execute the data loader. It actually loads the data.
So, what I like to think is like data loaders do the job of loading the data into the GPU and stuff. So the data loaders is a combination of multiple data loader objects. So each of the data loader has a job of getting the data onto the GPU. And data block is like a custom object that invokes this data loaders after going through a few processes. I like we had discussed in the first or second chapter where he had shown a diagram of what the data block does. For example, this get y, which there's a function runs which gets the labels, the get items, which is the x items, the images that we get. So data block does a series of steps, and data loaders actually will run the stuff on the GPU when we execute them.
So if I run this cell, like this data loaders,
Nothing will happen.
Nothing is happening yet, right?
Yep.
Yeah, that's what I thought. I just wasn't clear because I see all these transforms, and I remember in the other one we were transforming. My data was already loaded. You know what I mean? And then I could see it, squished and everything.
It's when you ask for, like, you run commands off of DLS that it'll do something. Like, for example, you can ask it to show batch, right?
Yeah. Can you do that? Can you walk through how to do that? Just do a DLS.
DLS in the previous step. So you have DLS, right? Just create a new cell.
Go ahead and there you go.
And then
Did you execute?
DLS.show batch. And that's when it actually executes something.
Is that a function? There you go.
Show underscore batch.
Oh.
There you go. That's when it does the fetching, the transforms. And by default, I think it gets it from the show batch. I'm trying to remember if it's getting it from the validation, I think. I'm not sure. I'm not 100% sure.
But then when I ran this, nothing happened, right? It's when I called
Nothing happened. It's when you run the show batch
this, yeah.
that it grabs the images and
That it
loads them
presses
and does
this
the
thing.
resize and does the transforms for each image and groups them and batches them and applies the augmentation transforms.
Yeah.
It's the name.
And it does it again and again. Like it's not a one-time thing.
So this has got a lot of stuff in it.
Man, does it ever.
Okay.
So that's a data loader. And it grabs it. Batch size 8. What is?
I think he does a good job explaining this one, though. I remember him explaining this
Boy.
in the video.
Yeah, this is where he was talking about the linear interpolation that takes place in the other systems and how they do it at the end instead of, if you look at the bear's legs,
Yeah.
you can really see how disformed the bear on the right is. And so they've come up with a better implementation on the left.
Yeah.
Does anyone know if there are any studies or anything out there of whether that makes a practical difference in applications?
Well, the thing is, augmentations is definitely something that most other libraries use. Like, there's a PyTorch library called Albumentations that's like doing it. Different, same things, warping. But the advantage, I think, for Fast.ai is that it's doing it on the GPU for a lot of these things. So definitely, augmentations help. That's an
Yeah. I meant like the when they were pointing out that the Fast.ai approach results in less distortion or something like that in the end.
Well, I think logically it would, right? Because a clear image would result in a better. And the fact that you're doing these things and it ends up distorting stuff kind of makes sense. That, yeah. But definitely in terms of speed, I've seen this because if you go back to the previous version of Fast.ai, Fast.ai's version 1, they didn't have this GPU accelerated batch transforms. They had transforms, but everything was done on the CPU. And it was much slower, even for the same data set especially. So definitely it's much faster. But again, I think it will, because remember, like, if you change it in a way that the model kind of learns the wrong thing, it does make more sense that even when you're augmenting data, it should still be similar to the data that it will see later on in production, right? So putting distorted things there kind of defeats that purpose, especially if it's repeated again and again across different batches. If it's on a random thing where it's like done once and it doesn't show up again, it probably wouldn't matter. But if it's being repeated again and again, I think the model will learn the wrong thing.
Yeah, that was my intuition as well. Thank you.
And, oh, we got cats. One dog. Okay, that's an error. Did anyone get this error in their thing?
I didn't run that yet.
Yeah. It's the thing
Yeah, I
that's,
did.
and did you figure out why?
I think it was because of different sizes. Yeah, so like the images being of different sizes would actually cause this error, and that's why we are all transforming into one particular size. So if you say they don't, the new data block that is done here, they don't transform all the images into one size, and down the line they are using the vector kind of this using a tensor stack or something, which basically expects the sizes to be same.
And if you notice, if you go back to the MNIST example, they didn't have a
Resize.
item TFMS, but it still ran okay. And the reason for that is because the input data for MNIST have all the same sizes. So that's why it doesn't trigger that error. But here it does, because the PETS dataset has different sizes. And the thing that will give you the clue, and this is very helpful actually, is trying to understand what the output of the summary is. Stepping through, like imagining what's going on with the data. So each line kind of helps you understand that. So it's not just like random stuff there. It's like really helpful to read what's in it.
So no one else ran this code yet?
I actually didn't.
Oh.
I got.
Yeah, I ran that.
Did you get an error?
Yeah. Yeah, I think it's supposed to have an error because the sizes are different, like Sam was saying.
Okay.
Okay.
Yep. That's the whole point of this, was to show you that there's an error and you should be able to try to figure it out what the error is just by reading what the output is.
Oh.
If you go down the line, especially
Yeah,
down the
scroll all the way to the bottom.
Yep. It says stack expects answers. But yeah. So one is size 374. The other one is 375.
Oh.
Yeah, one thing I was curious about on the inference side, and I don't know if this is the right place to talk about it, but looking at this error made me think about it again. When I was testing some of my new image stuff on the race car things, if I was using photos that were not already sized, my accuracy went down tremendously. I was just curious if anybody knows if it automatically downsamples images that you're testing to get it to the right size of what your model is looking for, or if that's something I need to look at manually doing.
Okay, I think it applies the same. You know how, well, later on we'll cover that, but if you're using the standard Fast.ai stuff, when you specify item TFMS and batch TFMS, it applies the item TFMS to both the validation and the transform. What do you call this? Sorry, it applies how we split it into a validation and training set, right? So it applies the transform slightly differently for the validation versus the training data sets or training data loaders, in that in the training data loaders, for example, when you do the batch transforms, you might have something called, I think it's covered down below, the random resize crop, where it takes out different spots of the picture if it's large enough. If it's larger than your image target image size, it crops out parts of it randomly. But that's what it does for the validation. For the training. But for the validation, it always takes the center image, like grabs the centermost part of the image, and it does it the same way again and again. And when you're using it for inference, it does the same transforms as the one that it uses for validation. So if you're during inference, it's going to apply, like, for example, if you do a resize 460, for example, it's going to resize all your images to something like 460. So it's applying the same.
Yeah, but I think the difference is that I resized all my images prior to any of the training part.
Okay.
So I get, but I didn't set that up for the inference side. So I think that's where the problem is, that I need to put a little function in to fix the resize.
So you resized it outside of the Fast.ai thing, or you're just calling the resize on the, you use the, what do you call this, the item transform, or you're doing it externally?
I was doing it externally in Python.
Okay. Yeah, then you should be doing the same thing for your inference. Yeah. Because you might
that
not
makes sense. Yeah. Because anything that's the right size, like I had, and I get, we talked about this a little bit before, but I get bummed up with the train, test, and validation sets, because like coming from like a scikit-learn standpoint, everything is test or train test split. So I'm used to calling what your internal testing, and it seems like we're changing that to now be validation, and then the testing is what goes on outside. So forgive me if I say this wrong, but so my train and test is what I considered my internal that my model saw, and then my validation was things that my model never saw. But then I went outside of validation and was downloading new things off the internet to use that were then not sized properly. So I think that's where my problem is.
Okay, so the idea is your validation set, the transformations being done on the validation set, like taking the, the way you're preparing your validation set should be what you should be using for your inference, is my general rule. So if you're doing the resizing inside Fast.ai, like there's a transform called resize, where whatever sized image you have in the wild is going to be transformed in Fast.ai to be used in my validation set, which is the one that gives you the metrics. Because the idea is your metrics should be a prediction of what it will see in the actual inference, your performance in the actual inference when you're using it in like production. So you should be doing the same preparation. So if you're doing the inference without resizing it outside, then you should be doing that in the same thing with what your validation set is doing, is get the same size, big images, whatever, and have Fast.ai resize it to something like the one that you use for validation during training.
Yeah, that makes sense. I ran into it today and haven't had a chance to really look at it. And I think that's definitely it, Butch.
But if you're doing it outside, then I would suggest during inference doing it outside as well.
Yeah.
Resizing.
I wonder which part of the image it was actually using.
Well, I don't have a resize function
Right.
on my Fast.ai, so
Yeah.
I don't know what it was using, but it was getting horribly bad accuracy.
Yep. Yep.
Yep.
Maybe
It's not probably using the resize. It's not resizing it.
right.
But that's why the reason why we normally have something like the item transforms will have a resize to something big, like the 460. And then during training, you use something smaller. Because in the validation set, what it does is it takes a center crop. So it takes, like, if you have an odd sized image, let's say 500 by 600, and you resize to 460, what it does is it takes the middle part of the, like, the longer dimension, takes a 500 by 500 of that, and then resizes that to something like what you resized it to. So it does a random, not a random, a center crop always for the validation set. So it always gets the same image across like different batches, across different epochs. It always gets the same image for validation. And that's what it does for your inference as well. It takes a center crop. So maybe that's the reason why it's getting bad images. So I would suggest doing a resize in your training, add a resize there, even if it's the same size. So if your image is, yeah, because it'll automatically apply that
Thanks.
during inference.
So in the time we were having that little side discussion, I just ran the learner, right? So I can run, and you can see the pieces there.
Yeah. So the point here is, I think this is one of the other things, like we're going down to like 0.07. Usually it's harder for me to interpret error rate compared to accuracy. I always get confused.
Yeah. Okay. Cross entropy loss is just another loss function. Is that it?
But this is the import. I mean, this is the whole point of this. I think this.
Multiple classifications.
Yep. So I would suggest working it through, understanding the difference between the MNIST loss and cross entropy loss.
Maybe that's something that we can spend some time on next week, since we sort of discussed not spending the whole 2-hour session on the ethics.
But there's no code. There's no code to run on the notebook for chapter 3.
Huh.
Just discussion, I would imagine. Okay, and then softmax. That's similar to the sigmoid function.
Yeah.
So that's what I was going to use when I thought I was going to do the full from scratch implementation of the MNIST learner, but I did not get that far. But I think softmax would be an approach to take for that.
Actually, it's a good exercise to apply that to like the two. If you already built it something and then go back and apply the softmax, that's actually
Yes.
a good exercise as well, because it should come out the same.
Right.
And then the log likelihood. Is it because we're moving away from the binary classification into multiple?
Well, it's that, and it's also, Andy, I think he makes a lot of comments about how it really punishes things that are not very good. So it puts some spread in what your predictions are.
Yeah, I think that's the point of the difference. I mean, the reason why it's using the logs to like magnify the differences. Sorry, the exponential rather.
Right. The opposite of magnifying.
Yeah.
It compresses.
It makes small differences bigger.
That's one way to look at it. Yeah. It allows large ranges to be usable into a usable range.
I think that's the log, right? But the exponential, there's a exponential part, the softmax, which computes the exponential so that small differences like a 0.1 difference versus a 0.01 makes a big difference when you take the exponential. So it kind of increases the numbers that you come out with are actually larger, even though there's like a 0.1 versus a 0.2 difference.
Right. It spreads it out.
Exponential, it's not double. Yeah, the difference between 0.01 and 0.03 and 0.01 and 0.02, it's going to be magnified when you take the exponential. And that's the reason why it's like forcing you to choose.
Yeah.
All right. I'm going to get these two at the end. And now taking the log. And then we just plot that. Here's where we stop.
And this is what I was talking about when I was saying, if you don't want it to be like, get the mean of all the cross entropy, you can say, I want to take the cross entropy loss for each sample. And this is what it gets.
So being that we're almost at the end here, I would say that since we don't have too much code in ethics, maybe we go back where Daniel said to go, which was where? Where was it, Daniel?
Honestly, for me, it's most of the chapter, but wherever we would benefit the most from picking this up on.
This was pretty dense. This last 2 weeks was very.
So maybe just go through this whole notebook again.
Yeah, I really focused heavily on chapter 4 prior to this. And then I quickly watched the lecture for chapter 5, but.
Just a heads up, I think chapter 4, 5, and 6, 4 and 5 in particular, are probably the meat of the mathematics. So 4, 5, and 6 for me was critical because understanding the loss function. The 4 is like really the groundwork for everything else.
So maybe we'll just try to work through 5 next week. Do we have any questions on the questionnaire? I didn't even look at the questionnaire. Sorry. Anything on the questionnaire there?
Put it up there.
Is it 4? 4 on 4, right?
I think, yeah.
And my thing still doesn't work.
What?
Is it just my
Why is that?
browser? maybe? I don't know. Let's see. No.
Huh.
That's weird. Okay. Well, never mind. I have it on another one.
Well, I had a question that I think was pretty, I don't know, it was kind of glossed over. I'm sure it's pretty fundamental to what neural networks are, but in chapter 4, when we defined the simple net, it had the 3 layers, nn.linear, nn.relu, and then nn.linear again. And we discussed the issue of, you know, the inputs being, the input of the first layer being 28 times 28, and then the output being 30. I guess I'm not clear on what's happening there. Do we have 30 different linear models taking those however many inputs it was and outputting, you know, 30 different outputs? Like what makes the 30 different things that are output by the first layer different from each other? Does that make sense?
Yeah. And yeah, and that's actually the thing that made me like figure out that's all it is. That's what deep learning is. Basically you have, so we start out with a simple one where we have basically one neuron, right? So we have, it's called a hidden layer. So you have 784 inputs, one pixel, one input from each pixel of the image. So in that, when we went to, and then it has a bias. So the neuron has associated with it a single number, a bias, which is a fixed thing that you add to whatever the weights are times the inputs, and you add like a single number to it. And that's the bias. And then that is then done, and then that, whatever that number is, you take the sigmoid of that, and that's your loss. And then you take the, what do you call this? And that's basically your prediction, is whatever number it comes out with, you take a sigmoid of that. So it translates it to a number between 0 and 1, and that's your prediction for whether it's a 3 or a 7. So that's the first example. The second example is where it goes through this, you have 30 kind of neurons in the hidden layer. Each one of them will have their own sets of weights, getting their inputs from the same image. And then they then go through this first stage where you have 30 outputs. And then they get to the next, what do you call this? The next layer, which has 30 inputs.
So just stopping you there a second, sorry. What are those 30 outputs from the first layer only different because the weights are initialized differently, or are they looking at different subsets of the pixels? Or I guess I'm not sure what's going on there.
Because they're initialized randomly.
Okay.
So in fact, one of the exercises that you might want to try is, what if you initialize them all to zeros, or set a certain value between 0 and 1, set them all to the same value and see if it trains.
Okay.
That's a good exercise actually to try to see. And it turns out, well, just a heads up, like the reason why it works is because they're initialized randomly, and they come up with a different set of like numbers, the gradient that compute them, and then you go through this process. And basically that's all it is. It's like the fact that you initialize them randomly, and then it tries to optimize it, and then it optimizes it differently, and then at the end it's like, whoa, it's good at computing this stuff. And that's all what deep learning is it starts out from random numbers, and then you optimize it, and then it comes out with something that's good at guessing whether it's a 3 or a 7. And that for me was the mind-blowing stuff. Like, what? Start with random stuff? And that's all it is. Yeah, plus add that ReLU, the breaking of basically take out the zeros. Anything below 0, take it out. And it was like, that's it? That's all it is. Yeah.
Is the second linear function necessary, or is it to get this universal approximation? Is it okay? do you just need the linear plus the nonlinear? What's the addition of the second linear in there?
I guess it's improved. What they found was more layers improves like the performance. Yeah.
Okay, but the minimum requirement is one linear function and one nonlinear function, right?
Yeah, but
Okay.
nobody you probably use that in the real world. So everybody's like doing 34 layers, 64. Yeah. So
I don't mean minimum. I mean just to, like he said, the universal approximation, the ability to model any problem if you have enough compute power.
yeah.
Is only because you have a nonlinearity in there. Without it, everything compresses into a trivial problem that won't do anything.
Yep. I think you're right. I'm not sure. I'm not 100% sure, but yeah.
I had a question regarding the redo function that we're using. So the purpose of the redo function is discarding the negative, right? If so if the weights turn out to be negative, it just moves them to 0. But like, aren't we actually discarding the data? Like, we are minimizing it. Like if there is a particular input, we are saying, okay, it doesn't affect much. But what if an input parameter negatively affected? May not be for this data, but what an input parameter actually negatively correlates to the output. So aren't we discarding that with the irrelevant? Did you
That's
get the
actually a
question?
good question. Yeah. So why? So that's actually a good question. I would like somebody else to take a crack at it.
I had the same question, but I don't have the answer.
Well, when you're saying negatively affect, what does that mean?
Like if you had a
So
85
so the
something, do you make it to 0? You know, if all your weights and everything for that particular output came with negative 85 or negative 90.
Right. It's still linear.
Yeah, that's what he's saying. He says, are we just saying we make a big negative number 0?
Yeah.
And then
Yes. You need to turn it off. You need to somehow.
but wouldn't that affect the results? Like, aren't we putting a bias into it? Like, just remove the negatives.
Yeah, that's
Like,
what he's
if something is like, so the negative point is basically saying that I'm not positively correlated with the output. If the output is increasing, I am decreasing, right? So which means it brings down the it's a negative correlation with the output. So if we reduce it to 0, we are just discarding. We don't take it into consideration. So my question was that doesn't that bias the output? The model doesn't that bias the model?
I think that's over our heads.
Doesn't it work just like a sigmoid function?
No, it's not. It's not our heads. It's actually a very crucial question. So, and the reason is, Siam, I think there are, well, at least if you go down further, what you'll find is that there are people who, or there are some neural networks that don't use ReLU. They use something called TANH or
Right.
something like ReLU functions that don't necessarily go to 0.
They get very small.
There's something called a leaky ReLU, but
You mentioned that in the video.
yeah. So there is I mean, it's not always the right thing to say, well, we take out all the zeros, but sometimes there are neural networks that use something called leaky ReLU that does take those negatives and add them to the output. It's just that the whole point of the ReLU is to add a non-linearity, because if you don't put that in, it's going to be linear, and it's just equivalent to one linear function. So the point there is to introduce a non-linearity to it. And I think what people find is that most of the time it works well. So I guess it's one of those things. But you're right. There are times where getting rid of that negative input is not the best thing. That's why there's people who use other activation functions.
Imagine that the tan H, for example, would make all the negative numbers be really, really, really small, but it
Yep.
wouldn't make them go to 0. So they would
Yep.
start to impact, but not like at the same scale as the positive numbers.
Exactly. Yeah.
Yeah.
So yeah, I mean, from an intuition sense, that's the idea for
It's
all
still
these
it's still nonlinear in a to a large degree.
Yeah. But you're right. Actually, that's why I was saying it's actually a good question. So it's not an automatic thing where we always use rel use.
As a matter of fact, in Andrew Ng's course, you use all of them. You use tan H and other activation functions. You end up doing a lot of ReLU and moving forward with it.
Yeah, but that, I think in terms of practice, real world stuff, people find it most of the time. So that's the reason why.
Well, we should throw it in. I'm sure Fast.ai has the tan H right there. We should throw it in.
And I think you can create your own like networks and not use rel use. Definitely.
Well, yeah. I mean, Daniel built his little learner. He could have pulled in the .tanh function.
Yep.
Just as easily.
Yep.
Yeah, I guess that would actually be pretty easy for me to try. So maybe I will take a look and throw it in the Slack channel.
I think that's what Jeremy is always emphasizing. Play with the code, experiment, and do a lot of your own experiments, and then tell them to everybody else, like, hey, I found this thing and it doesn't work, but yeah, this is what I found. I mean, it's still learning. Yeah.
All right, guys, it's 7:34.
Thanks for that.
Lots of good, interesting conversation. Thank you for joining this evening. I will see you next week.